So in the previous video and in the pencast, we've looked at homonuclear molecular orbital diagrams. So now we want to take a look at heteroatomic molecular orbital diagrams. So that means we have two or more different atoms. So I'll share my slides with you. And here we go. All right, so we'll take a look at these. So we'll look at two examples, lithium fluoride and the bifluoride ion. The process is very similar to that for the homonuclear diagrams we've drawn before, but once we start changing the atoms, now the energies of the atomic orbitals are no longer the same. This diagram shows the relative orbital energies for atomic orbitals of periods 1, 2, and 3. So the first molecule we'll look at is lithium fluoride. So let's examine the energies of the 2s and 2p orbitals for these atoms. Lithium, which is shown right here, has a 2s orbital with an energy of negative 5.4 electron volts. The 2s orbital for fluorine is way down here, and it has an energy of negative 40.2 electron volts. These are very far away. The 2p orbitals for fluorine, however, which are in this line here, so are about negative 18.7 electron volts. Since we know that lithium fluoride exists, let's consider what would happen if the lithium 2s and the fluorine 2p orbitals interact. So taking the information from the previous page, we have this diagram. For lithium, the atomic orbital that is available to participate in bonding is the 2s with an energy of negative 5.4 electron volts. It contains 1 electron. The fluorine orbitals are shown on the right with both the 2s at negative 40.2 electron volts and the 2p at negative 18.7 electron volts. Now we will consider a combination of the atomic orbitals. The 2s orbital from the fluorine atom is very low in energy. It is so far from the lithium 2s orbital that they cannot interact. However, the 2p orbitals on the fluorine are close enough to the lithium 2s to interact. And as we said before, since we know this molecule exists, we'll go ahead and consider what happens when the 2s from lithium interacts with the 2p from fluorine. The only orbital from the fluorine 2p set with appropriate symmetry to interact with a 2s orbital is the 2pz. Remember that s orbitals do not overlap with the px and py orbitals in a way that results in overlap, at least at this diatomic level. So the 2s orbital from fluorine is the lowest molecular orbital. So this orbital really doesn't interact with anything else. It's still there when we have the molecule, and it has 100% fluorine character. It doesn't interact with lithium at all. It is designated as a sigma symmetry because it came from an s orbital, so it still has that cylindrical symmetry. The lithium 2s orbital and the fluorine 2pz orbital overlap and produce a bonding and an anti-bonding molecular orbital. So that's this bonding and anti-bonding orbital. The remaining 2p orbitals from the fluorine do not interact with any orbitals on the lithium and are actually 100% fluorine in character still. Note that if we want to determine the bond order in this case, we'll consider only those orbitals that are interactions between the two elements and not those orbitals that are 100% fluorine in character. Let's quickly look at one other example, and this is for not a diatomic like we've been looking at, but this is the bifluoride ion, which has 3 atoms actually, and a charge. Remember what we do when we have a negative charge on an atom? Right? We add another electron. So if we were drawing the diagram from scratch, you need to remember to add that extra electron in. So this diagram shows the hydrogen 1s orbital on the left. That's the only orbital available to hydrogen to participate. And we have 2 fluorines. All the atomic orbitals from the fluorines are shown on the right. So we have both of those. The fluorine atoms interact with each other, especially if you look down here at the 2s orbitals, and so generate bonding and anti-bonding orbitals from those interactions. And you can also see that the 2p orbitals interact with the hydrogen 1s orbital. There are also some orbitals that don't interact with hydrogen and are then 100% fluorine in character. So once we start getting into drawing diagrams for heteronuclear diatomics or more complex molecules, things get pretty complicated, but we can really use these models to understand what's happening in sort of real-world examples. It takes a little practice, so it's a good idea to go through these and practice them, and also look up other molecules and try to draw your own diagrams. You can use the graph that was one of the first slides in this set as an estimate of what the individual atomic orbital energies would be. All right, so that's it.